Previously, we have only considered torque as applied to an object spinning around a fixed axis of rotation, or rolling. Now we're going to consider, can we apply the idea of angular motion and torque to an object simply moving through space? So consider this apple right here that is falling from a tree. Does it have any sense of rotational or angular motion to it? Well, if you're a bug sitting on this apple right here, all you're going to see is the apple falling straight down beneath you. There would be no sense of rotational motion whatsoever. On the other hand, if you're standing to the side over here and you watch the apple fall from the tree, to keep your eye on the apple, notice you would have to move your head or rotate your head. If we let your eye be the origin of the frame of reference to describe the motion of the apple, we would start by looking up here, and then we would have to rotate our head to look down there, and in a sense, the apple has indeed moved through an angle. It would take a certain amount of time to move through that angle. Therefore, we in fact could calculate an angular velocity by the change in angle theta divided by the amount of time that took. So in a sense, it does in fact have angular motion. However, how much angular motion it has depends on your point of view, or if you will, your frame of reference. The bug up here would say, no, it didn't move through any angle, it just moved straight away from me. There was no delta theta, and therefore no omega. Person standing over here would see a movement, an angle, and it would take a time, so he could calculate an omega. Which shouldn't be too surprising, because we know that all motion is relative. That includes not only translational motion, but also angular motion. Now let's consider the apple's motion. Is it, in any sense, a constant motion? And the answer would be no, because the apple is going to speed up as it falls, and the angle it passes through would be faster the closer it gets to the ground, the faster it's moving. So therefore, it would also have, in a sense, angular acceleration, which is to say, the angular velocity would be increasing as the apple fell, and it would therefore experience some sense of angular acceleration. But that would tend to imply what we've already learned, that there must be a torque applied to the apple if the angular acceleration is not zero, because torques are what cause angular acceleration. If it's in free fall, then the only force acting on the apple would be gravity, and torque is r cross f. What exactly would r be here? Before, r had something to do with distance from an axis of rotation on an object spinning around a fixed axis of rotation. But in fact, r is just a vector that goes from the axis of rotation to the point of application. Well, the axis of rotation, we could say, is u, you're the point of reference, and it goes to the point of application, and that's the apple. So r would be a vector going from u to the apple, and we could then calculate a cross product between that and the apple's weight. So, yes, in effect, there is a sense of a torque applied to cause this angular acceleration. Does that mean it must have a moment of inertia? And notice here, the moment of inertia would not involve the apple spinning around its center of mass, because it's not rotating around its center of mass. Instead, it's rotating around u. So the moment of inertia, which is I equals mr squared, m is the mass of the apple, r would be the distance from the axis of rotation, which is u, to the apple. And we could calculate a moment of inertia. M, mass of the apple, times the distance between you and the apple. But notice as the apple falls, r will vary. So the moment of inertia will vary. Okay, but that's fine, because the torque will also vary, because this angle between the radius vector and the force vector would also change, as would the angular acceleration. So how can we explain what's going on? Everything appears to be changing. Torque would be r cross f, which would be r times the force, and this right here is the component of the force that is perpendicular to r, which is one way to calculate the torque, r times the perpendicular force, which would be the weight, mg, times the cosine of this angle right here would give me the component of the force that is perpendicular to r. It's negative because notice this is a clockwise torque. Moment of inertia is just mr squared. The angular acceleration would again be the tangential acceleration, which again would be acceleration down, which would be vertical, times the cosine of this angle right here would give me the component of the acceleration that is perpendicular r. That gives me the tangential acceleration. That is, if you remember from rotational kinematics, what gives us the angular acceleration. So a times the cosine of theta is the perpendicular component of the acceleration, divided by r would then give us the angular acceleration. Plug that all into torque equals I alpha. So we replace torque with this expression, replace I with this expression, and we replace alpha with that expression. And then we will note that the cosines are on both sides. They cancel out. One of these r's cancels that r. The other r cancels that r. This m cancels that m. So everything on this side of the equation is gone except the minus sign and the g. Everything on this side of the equation is gone except this a. So therefore we get the unsurprising result that the acceleration is simply minus g, or indeed the apple is indeed in free fall. All we have now shown is that the equation torque equals I alpha doesn't just describe the motion of an object spinning around a fixed axis. It also can be applied to an object moving freely through space, even if it is not spinning around its center of mass. Torque equals I alpha can be used interchangeably with F equals ma. It may seem like a really odd and weird way to describe the motion, but it does just work, which is what we just showed. Now, we will be computing cross products, so it's worthwhile remembering how we compute cross products. So torque is r cross f. There are three different ways to view it. One is the magnitude of the radius vector times the magnitude of the force vector times the sine of the angle in between them. That's one way to do it. We can also find the component of the force that is perpendicular to the radius vector, and that would just be f times the sine of that angle. And that gives us this definition. We could just say that's the component of the force perpendicular to r, because the rest of the force would basically try to stretch something rather than make it rotate. Or we could take the force, draw the line of action along the force, and find the perpendicular distance between the axis of rotation and that line of action. And this is essentially the lever arm. So the lever arm times the force could also be seen as another way to calculate the torque. In addition, we also can calculate the torque as a literal cross product by calculating the determinant of this matrix, which is computationally more complicated, but if we do have the r vector and the f vector in IJK format, we can compute this expression right here. It can be cumbersome, but that also is another way to calculate a cross product.